So I'm at Los Alamos National Labs right now, but a lot of this work was started when I was at the University of Michigan, and it's been continued with my collaborators, Christiana and James Kent, who are in the audience, and Ricky Rude, who's primarily at Michigan. And this is the paper that has recently been submitted to QJR that talks about our results. So this is an overview of what I'm going to be talking about. First, I'll talk about potential vorticity, what it is, why we care about it in general. I'll talk about general circulation models and a description of the 4 dynamical cores that we investigate. And then I'll look at the baroclinic wave test in particular and how we use potential vorticity incorporated in that. And then I'll look at some of the results. So we're interested in Ertel's potential vorticity, and this is his original abstract, or a piece of it here. And my German pronunciation isn't very good, but I was told this is what the title is in English, a new hydrodynamic conservation law. In essence, what Ertel did, and this is based on some former work by Rossby, is you take the total vorticity here, this is the zeta, and I guess the absolute vorticity in this context, dotted into the gradient of the potential temperature. And this quantity Q, which is defined as the potential vorticity, is conserved following the flow. And this is the reason it's interesting is because it's a new conservation law that we can derive. This paper, just to give us an idea of how important it is, according to Google, a couple weeks ago at least, it was cited over 1,500 times. So that usually indicates that it's a useful paper, and it's titled "On the Use and Significance of Isentropic Potential Vorticity Maps." One of the things that they point out here in the summary, they talk about the invertibility principle states that if the total mass under each isentropic surface is specified, the knowledge of the global distribution of PV, or potential vorticity, on each isentropic surface and of the potential temperature at the lower boundary is sufficient to deduce diagnostically all the other dynamical fields such as winds, temperatures, geopotential heights, etc. under a suitable balance condition. So essentially, potential vorticity is important. If we can follow potential vorticity, if we understand it, we can understand the other dynamical variables. So now I'm going to give a very brief overview of the 4 dynamical cores that in INCAR CESM that I'm going to be talking about. And I think in this field, there's always going to be acronyms and definitions. So this is just a list of a couple of them. I'll just let you read them. So the 4 dynamical cores I'm going to be talking about are the CAM semi-Lagrangian, the Eulerian, finite volume, and spectral element. Now we've heard quite a bit the last couple of days about the spectral element. Now it's the next generation. It'll be the next default dicore in CESM. The finite volume one is previously was the default dicore. It was based on a latitude-longitude grid, a finite volume, excuse me, obviously discretization, and its form of dissipation is primarily the small-scale noise control by divergence damping, a type of diffusion. The Eulerian and semi-Lagrangian dicores are based on a spectral transform model, and they both employed hyperdiffusion. The tracer advection was significantly different in both of these in that for the Eulerian model, it was dimensionally split semi-Lagrangian, but for the semi-Lagrangian model, there's no dimensional splitting. That affects things slightly, but as you'll see, the results for those 2 models are pretty comparable. So the specific runs I did here, what we were interested in specifically is what happens on the subgrid. So what happens when we don't resolve things? Because in climate resolutions, there's a lot that happens below the grid that we can't see what's happening. So these are pretty coarse resolutions. For the finite volume, we ran it at 2 degrees. For the Eulerian, the spectral truncation was at 85. So as you can see, there's a few more grid points for the spectral transform models. The effective resolution was a little bit higher for those. And then for CAM-SE, we had a 16 by 16 grid on each one of the faces of the cube. which corresponded to just about the same resolution as the 2-degree finite volume one. And these are the time steps for the tracers and the dynamics, as well as the diffusion coefficients. That's included in the paper for comparisons. So what we did is we took the baroclinic wave test case, which was developed by Christian and Dave Williamson in 2006, and we're going to modify it slightly. So this test case, I'll just cover the first paragraph in the summary. It's an initial value test case for a dry dynamical core, so we don't have any physics turned on. We're trying to make this as simple as we can. And the idea is that you have an initial zonal state, which is quasi-realistic and completely defined by analytic expressions. So it's repeatable, which are a steady state solution of the adiabatic and viscid primitive equations. And what we follow, in this paper, they have a 2-component test strategy. What we're interested in is when you overlay a perturbation onto this wind field, which eventually triggers the growth of a baroclinic disturbance over the course of several days. And that's what we're going to be looking at. So from that 2006 paper, if we look at some of the development of this baroclinic wave, so on the left, and it cut off a little bit on the title here, but on the left is the surface pressure, and here this is at day 4. Day 6, you can see the wave is developing. There's some interesting things happening. Day 8, it's getting even more structures is coming, and by day 10, the wave is broken, and there's quite a bit happening. And over here, this is the temperature field at 850 hectopascals. And this is, again, at day 4. It looks pretty mild. Day 6, you can see the wave developing, but again, it's relatively mild. Day 8, the wave's fully developed, and by day 10, it's broken, and the nonlinearity is fully present. So this is the test case that we're going to be investigating. So the modification that we're going to do is to introduce a passive tracer that doesn't affect the wind dynamics to this Jablonowski and Williamson test case. And this tracer is going to be initialized as the exact initial potential vorticity, which we can compute precisely because we have analytic initial conditions. Now, and then from there, as the flow evolves, we can also compute the potential vorticity from the dynamic wind and temperature components. And we're going to call that the dynamic PV. This initialized tracer we'll call tracer PV. And in theory, those two should agree exactly. Because we've turned off the physics, this is an adiabatic test case. And then we can compare the two and see how well the model compares between tracer advection and dynamical evolution of the winds. And so this is the idea that we're going to use going forward. We're going to do this for all 4 of the dicores. So the difficulty lies in computing the dynamic potential vorticity. So in the hydrostatic case, which is what we're interested for all 4 of these models, this is the definition of the effective definition of the potential vorticity. And the difficult part that you see here is that we have a gradient of the potential temperature. And the reason that that's difficult is that if you look in so this is a plot from the Jablonowski and Williamson paper in which they plot the isolines of the potential temperature, and you can see that as you move upwards in the vertical direction, especially near the top of the model, the potential temperature varies quite rapidly. And so computing derivatives of the potential temperature can be very difficult to do. So I spent quite a bit of time playing with that, trying to find different ways to make sure I was happy with the way I was doing that. And eventually I was quite surprised to find that if I interpolated the potential temperature onto a cubic spline in the vertical direction and used that to compute the vertical derivative, it did extremely well. The errors were very minimal. And just to give you an idea, I did a plot. I changed the number of vertical levels in the model, and I took the initial analytic data where I could compute the PV exactly from the analytic initial conditions, and then I used my method that I'd come up with to numerically compute the PV as well. That way I can compute errors. And so if we move to the 315 Kelvin isentropic level, then this gives us the percentage errors of the potential vorticity computation. And because, and this is where I just did a plane-centered finite difference, and you can see the comparison between that and the cubic spline. And the errors are significantly better with the cubic spline. And because of that, I also chose to use 52 vertical levels for all 4 of the dynamical cores, just because then I'd have better resolution to compute this vertical derivative. And these levels are computed as the midpoint levels between the old default levels for CAM4. And that's just because that's what, at the time, that's what seemed the natural way to do it. So now if we move on to the results, and unfortunately, I think you can't see the one of them as well. So this is the percentage, so this is the percentage, not the actual error, of the inconsistency between the dynamic and the tracer PV. So I broke this up into the first 7 days, basically when the flow is pretty linear, and the wave is just barely developing. It's not very exciting. And then from day 7 to 15, and you can see, when the wave breaks somewhere right around in here, that the errors all grow quite substantially, which isn't surprising. We would expect that. The flow becomes nonlinear at that point. And what you can see here is that the 2 spectral transform models, the red and the purple, do relatively similarly, both for the linear case and for the nonlinear case. And the finite volume model does a little bit better in the linear case, but again, we're looking at less than 0.1% of inconsistency, which is not very remarkable. The one, and I don't think you can see this as well, unfortunately, the green one here, I don't know if you can see, this is the spectral element, and the reason it starts, the inconsistency error starts up here is because I wasn't able to, or I didn't have the time to work out the PV computation on its native grid on the cube sphere. So I interpolated it to a lat long grid before I did these computations. And so initially it has a little bit higher error. But again, we're looking at something that's 0.14%. So it's okay. I'm okay with that. But surprisingly, even with that greater error initially, the spectral element model does considerably better once the flow becomes nonlinear. By day 15, the final errors are less than 3%. So now the key thing about this, though, is that I'm looking only at the isentropic level at 315 Kelvin right now. And I'll explain that towards the end. So another way that we can look at the errors to give us an indication of what's happening is to look at scatter plots. So we can plot the dynamic PV at each point in the model that it gives us on the horizontal axis here, and then we have the tracer plotted on the vertical axis. Now in theory, they should be equal to each other. So they should just give us the line y equals x. Like at day 1, all of the models seem to do that relatively well, because not much has changed since the initial condition. But as time evolves, things get a little bit different. And this gives you an idea of where the differences arise, rather than just a simple error norm. For example, if we look at day 15 up here, so we're looking at the very largest values. You can see for the finite volume one, as well as for the, and I only plotted one of the spectral transform models because the plots are pretty similar. But you can see that for both the finite volume and the spectral transform model, the dynamic PV particularly had more large values in this region than the tracer. Whereas the spectral elements seemed to not, there wasn't as much of a bias one way or the other. And you can make similar observations there's other things you can say about the other regions, but I'll point you to the paper if you want to look more in that. So this is at day 15, I plotted at the 315 Kelvin isentropic level. The potential vorticity on the left is the dynamic PV, on the right is the tracer PV. And there's a couple of things I want to point out about these different plots rather quickly. So first off, you can see that in the dynamics, there's a little bit, I don't know if you can call it noise or finer detail structures or something that's represented in this region that doesn't show up in the tracer. And the difficulty with this test is that we don't know which one of these is right. An easy way maybe would be to say it's the average of the two, but there's no scientific reasoning for that. But there is differences, and you can see that significantly. And this may be what we're seeing in the spectral transform models. This may be part of the reason we were seeing that the dynamic PV had significantly larger values in that one region I pointed out in the last slide. So another area that's particularly interesting is to note that the finite volume and the spectral element dichord, there's this, between these two contours here, there's a definite gap, whereas that gap is smaller in the spectral transform models, both for the tracer and for the dynamics. And another way to look at it, and I won't dwell on this, it's detailed in the paper, is that you can plot probability density functions for the tracer and the dynamic PV, and you can compare those as well. In theory, because especially up to day 15 for this test case, the northern hemisphere is invariant, then the probability density function of the PV, whether it's tracer or dynamic, in the northern hemisphere should stay the same for all time. And you can see there's changes here. And you can look at the paper if you're interested more. But the thing, I'm sort of sweeping something under the rug. Why have I only been looking at isotropes at 315 Kelvin? And the reason is, so if we look at the potential vorticity plotted at different isotropes, so on the right is 315 Kelvin, on the left is 300, then they vanish right here because for isotropes just a little bit lower than 315 Kelvin, they intersect the surface. And something appears when that happens, when the isotrope intersects the surface, something appears to go, as I put, horribly wrong. So this is a plot of the potential vorticity interpolated to 285 Kelvin. And this is just like the plot I showed earlier, except now we're looking at 285 Kelvin. Now here you can see something really doesn't look quite right. So for example, in the tracer PV for CAM-SE, here we have a low, and here is just a bunch of noise that looks like it's actually a high now. If you look at some of the other models, especially where the isotrope intersects the surface, you see that the dynamic PV gets all this red value, which if you look over here is extremely large. And this happens, you can see it's for all four of the dichords. It's a little less distinctive for CAM-SE where the isotropes intersect the surface, but it does happen for all four of them. And this is just to highlight that region here. So you can see where it is. So these results like this, where the isotropes intersect the surface, this is pretty robust. Like I said, it happens for all four of the dynamical cores. And it's not just because I was looking at extremely coarse resolution. I've ran this for higher resolutions for a couple of the dynamical cores. I haven't thoroughly investigated all four of them at higher resolutions, but the ones I have, it's even more noticeable at high resolution. So it's not necessarily a question of resolving things adequately. So I have a video I'd like to show that gives us a better perspective on how this develops. But before I do, the movie I'll show is a 1x1 CAM-FV run, and I used 120 vertical levels, which I kind of came up with. Basically, I stacked all the levels near the surface because that's where the interesting stuff happens. And this is just so I can make sure I was really resolving vertically what's going on. And that wasn't what the problem was. What we're going to be looking at is a longitudinal vertical cross-section at 50 degrees north because we can see a little bit better what happens. And I'll have the dynamic PV on the left and the tracer PV on the right. What we're going to see is that there's a static instability that develops locally. And when that happens, you'll see blue values of the PV show up. And that corresponds to the static instability. And shortly afterwards is when we get the interesting stuff. So you can see the blue, this is the static instability here. So you get negative values of PV showing up in the dynamics. Again, this is the dynamics, this is the tracer. And then shortly after we have the static instability, you see the sharp, large red values showing up. And as you can see, nothing like that is happening in the tracer over here. And as the flow progresses, it just gets worse and worse. But this gives you an idea of how things are developing. And the same type of thing happens for the other 3 dynamical cores. I'm more familiar with CAMFV, so I knew how to play with things more. And that's why I did this particular run this way. But you can see at this point that at this snapshot in time, the tracer and the dynamic PV definitely don't agree with each other. So as far as what that means, I was told once not to conjecture while you're giving a talk, so I won't. I don't really understand what's going on there yet. We have some ideas, we're working on it, and I think it should be interesting to find out what exactly is going on. And part of the way we're going to do that is to use some of the data that was collected at the recent Dynamical Core Model Intercomparison project, because there's a lot of different models there who perform this test. And if we can look at the data and see which models, if the same issues arise, if there's some of them that don't, maybe we can understand what's happening here. And so for more information about that, you can see James or Christiana's talks this afternoon. But that's all I have.
Could I say, I think this is very important because even more in the ocean, you get the same effect of static instability when a baroclinic eddy wraps up. And this has to be added to the list of diapicnal mixing mechanisms in the ocean. It hasn't been recognized, I think, apart from me banging on about it for some years. I think it deserves a name, and this is the first evidence I've seen of this in a numerical experiment, thanks to modern high resolution. The name I've given it provisionally is DIMBO, which doesn't mean stupid, it means diapicnal mixing by baroclinic overturning. And this is certain to be important in the ocean. It's on my webpage if you want to see a little talk about it.
I was going to come back to these errors you saw at the other Kelvins. I didn't quite understand your physical explanation, but from a mathematical point of view, are you sure your calculation of the PV is accurate?
I spent a lot of time on that, really, and I don't think there's much I could do more.
But the cubic spline one that you had, what worried me was when you actually increased the number of points, your error didn't go down.
Oh, okay, so okay, I think I know what you're talking about. So the reason for that, I meant to mention this when I went to it, right here. The reason for this, so like right here.
Yeah.
So I think because if we look at 52 vertical levels, then one of the levels lies very closely with this isentrope. And then if I split the number of points again, then they move further away from it.
Maybe a different part of the question is, don't you normally need to solve a global equation to find potential vorticity from the other diagnostic variables? I mean, what's your Coriolis parameter? Is it constant or is it actually varying?
No, it's varying with latitude.
I will conjecture on what you're seeing. Once collapse, dissipation should produce PV. It should be a source term, and that source term doesn't show up in your tracer transport. You don't have a source term in your tracer equation, this PV that you're vectoring around. So the fact that the two differ after you see frontal collapse and the waves break should be expected. They have to.
Okay. Yeah, I don't know.
So I say that's not error. That's the dynamics of the problem.
Just one other remark to this slide. This nearly constant error for the cubic spline is this determined by the inaccuracy in computing the horizontal vorticity?
Yeah, so the horizontal vorticity is computed by,
discretized, so it has some discretization error.
yeah, there's some error in the horizontal computation, and that may be why we're seeing, and it could also explain why these don't change much.
Yeah,
because
that tells us just that with the cubic splines, the discretization error in the vertical doesn't make a significant contribution.
yeah, at this point, yeah, so that's good.
Or you could test this hypothesis by doing the horizontal analytically and the vertical numerically.
Yeah, and I did look at that, and that's how I decided the cube spline would work the best. I don't have the numbers for that. But.
I'm afraid we need to move on. Maybe can you talk to Jared after the coffee break? Our next speaker is Peter.